Hello everyone, welcome back to the latest lecture session. A quick recap of what we have been up to. We have been discussing the relevant aspects of biological treatment, right. In that context, we looked at different kinds of biological treatment and what are the different compounds or the process that are relevant. For example, we know that organics or organic BOD or BOD needs to be removed. We looked at nitrification and denitrification. We looked at phosphorus removal. These are the four major processes typically that we are concerned with. In that context, we started looking at activated sludge process. In that context, we looked at how do microbes grow, or what are the equations that can help me understand how these microbes grow, what are the rates of microbial growth, right. So, we looked at that, and we looked at two cases when the food or our waste or the substrate is high, when it is low, so on and so forth. We looked at that, right. So, we will have a quick recap of those aspects too, but in the context of what we are going to discuss today, I need to I guess refresh your memory regarding some aspects. We are going to understand how to analyze or design the activated sludge process, or for that matter any process, any biological process, let us say. We are going to use some terms which we are going to look at, fine. But as discussed in the initial lectures of this course, we saw that when we are analyzing any process or unit process where different compounds come in along with some flows, they leave along with some flows, and they are being transformed within some or due to some reactions, let us say, right. How do we analyze this system? How do I design such systems, let us say? How do I make sense of it? So, to be able to make sense of it, we understood that, or we applied the principle of mass balance, right. So, mass coming in, mass going out, and mass being transformed. So, these three aspects will give us an idea about whether the compound is accumulating within the reactor per time or with time, or it is decreasing with time, let us say, right. So, let us consider these aspects. Again, ladies and gentlemen, the key aspect is mass balance, right. So, you will use that throughout environmental engineering and certainly in water and wastewater treatment. So, thus we already discussed three kinds of ideal reactors and applied the mass balance earlier in the course, right. So, we will use those principles here. Again, we are going to look at some derivations. In general, we do not go into detailed derivations, right, because this is an UG course, pardon me. But here we are going to look at the derivations in some detail, but again these are not complex derivations. It is just mass balance, mass coming in, mass going out, and mass being transformed inside the reactor. Why do we need to look at these derivations? Because many plant operators or many people out there, let us say, do not look at the underlying assumptions before applying the formulae. And obviously, as is the case with any formula, you are going to have different assumptions out there. So, without understanding the underlying aspects, if you apply the formula, right, you will face one stumbling block after the other. So, in this particular aspect, which is crucial to biological treatment and thus to wastewater treatment, we are going to look at mass balance in understanding how things work, and then to help us design the relevant systems, let us say, right. Let us move on here. So, analysis. So, I know that I have my head works or preliminary treatment, right, and then my primary treatment where I am removing the, let us say, preliminary treatment, primary treatment, right. And now here I removed some BOD, maybe 30%, 35%, right, or less than 35% BOD removal, maybe 70-65% suspended solids were removed, right, maybe 70 or 65%. So, here you are still left with a considerable organic content which is dissolved primarily, and you want to remove that. So, how do we remove that? As mentioned, we are going to use microbes and we are going to provide oxygen, so that the microbes use their enzymes or catalyze this particular degradation of our waste or their food with the relevant enzymes, right, and you are going to fasten or improve the kinetics. Again, we saw that microbes use the compounds or our waste for two processes. One is for energy generation, one is for cell synthesis, and the electron acceptor in the overall reaction, if I may say so, is oxygen, let us say. So, that is one aspect to keep in mind. So, what happens here in this biological process? You know that you have to give oxygen input, right. There is not enough oxygen in the wastewater obviously, and you are going to have the microbes out here, and they are going to, while using or consuming oxygen, degrade your waste or their food, which is the substrate. And then the kind of microbes that are going to be formed, they can be settled down and removed from the system. If not, you will have issues with microbes or high microbial concentration and again organics leaving the system. So, the supernatant will be clear, and here let us say this is the water, let us say the supernatant will be clear, while the flock forming microorganisms which are relatively heavier, they are going to settle down. So, these we will send to treatment. Again, why? Because again organic content, cells, right, again cells, organic content, you can't just throw it out there, it is going to lead to relevant issues, septic issues certainly. So, you are going to have to stabilize it or degrade it, right, into more stable compounds, but we do not always waste it. For example, this is the waste, we do not always waste it. Why is that? Here in our sewage or in our waste, we have some microorganisms, but the kind of microorganisms that lead to the degradation of our waste are not typically present. What microorganisms are present here? We do have microorganisms coming in, but they are enteric microorganisms which are not going to assist in degrading our waste. So, where will the source of microorganisms within this aeration tank? Why aeration? Because I am providing air which will contain oxygen. So, I am going to recycle part of this sludge which has settled down, right, that thus it is called the activated sludge process. Depending on the need, some of it will be wasted, right, and here I am going to get my treated water. So, that is the process, and we are just applying this or going to look at this part of the system today, right. So, this part of the system we are looking at it today, and where do we see that? Here we see the figure out here. So, this is the aeration tank, this I guess is a poor figure, but again you understand the typical shape that you want, right. And here you have, what do we say, here you have the secondary clarifier or secondary sedimentation tank, right, where you separate the sludge or the microorganisms from your wastewater, let us say, right, which is easy to do because they are not dissolved obviously. So, the settled sludge is either going out as waste or is recycled back into our aeration tank, so that you provide or we have enough microbial concentration inside the tank. If the concentration of microbes is too less, obviously the kinetics or the rate at which these microorganisms can degrade the relevant wastewater is going to be very slow. If it is very slow, then you need a huge volume of tank, which is not feasible. So, these are some aspects. Let us just understand the variables. So, I guess subscript O indicates influent, sometimes we write it as in, at least I write that, right, and subscript R indicates recycle, as in this is from the recycle flow, recycle, and W indicates wastage, what is going out in the wastage. So, let us just understand this. Wastewater with a flow rate of Q, which has R waste at an initial concentration of S naught or S in. S stands for substrate, R waste, organic compounds, let us see, right, which need to be degraded. X naught stands for the initial concentration of microbes. In general, depending on the type of wastewater, X naught is typically 0. Though there might be microbes, they are not the microbes which will lead to degradation of waste. So, this is a pretty good assumption. So, X naught is typically 0, okay. This is the concentration of microbes coming in along with the wastewater. So, what is happening here? Inside the tank we have substrate, microbial concentration and volume of the tank. These are the variables that we are concerned with. We will look at other variables too. So, here we see that now the flow rate is not just Q, it is Q plus QR. Why is that? We know that some of the settled sludge, right, which is the microorganisms, are going to be recycled back. Why is that? Because you need a high concentration of microbes, that is why. So, Q recycle or the rate of recycle flow is QR, that is why we have a flow of Q plus QR here, and concentration S and concentration X out here of the microbes. They go to the secondary clarifier, right. Here again, here there are little to no reactions occurring. Why is that? Are we providing any oxygen here? No, we are not. First, turbulence, that will not meet the purpose. Whatever oxygen is required, we are providing that right here. So, there is no oxygen being provided out here. So, the assumption which typically holds good is that the substrate, whatever is coming in, will not be degraded in the secondary clarifier. We are only removing the sludge or the microorganisms or changing phase, let us say, right. They were earlier suspended in the water, the microorganisms, and these flock forming what do we say, microbes, they are going to settle down. That is what is going to happen here. And part of the sludge is going to be wasted, sent for stabilization or recycled to increase the microbial concentration. And obviously, Q minus QW is what we have out here, let us say, right. So, I should not have just said Q minus QW, but that is fine. We will look at, right, Q minus QW is the right answer out there. Okay. So, this is the system. Let us understand how to analyze this. Some terms which I already mentioned, Q flow rate, right, coming into the tank. So, it is volume per time, let us say, volume per time. So, microorganism concentration entering the tank. So, MLVSS, different ways to measure, we will look at that later. Microorganism concentration coming into the tank. Sometimes I use X naught, sometimes Xn. Okay. Volume of aeration tank, okay. Again, volume of aeration tank, not of the secondary clarifier. Why is that? Why are we not really looking at that? Because we are assuming that there are no reactions occurring within the secondary clarifier, because we are not providing any oxygen to the or into the system in the secondary clarifier, right. And without oxygen, you will not be able to, or the microorganisms will not be able to degrade the relevant waste or the substrate. Mu, right, specific growth rate constant or maximum specific growth rate constant, which will give us an idea about the microbial growth, right. We will look at that again later. S is the waste or waste and food for the microbes, which is referred to as substrate. Yes. X again, depending on where we use it, it is the concentration of microbes. Ks is the half velocity constant, which we came across when we said looked at this Monod equation, mu is equal to mu max into S by Ks plus S, right. So, this is what we have. We will look at this again later, or it is typically going to be equal to 1/2 the maximum growth rate. Soluble BOD5 concentration not equal to 1/2 the maximum growth rate. That Ks is equal to the soluble BOD5 concentration, that gives half the maximum growth rate, right. And what else? Decay, rate of decay, because microbes are going to decay or degrade. Wastewater flow containing the microorganisms that needs to be wasted, this will depend upon the mass balance. Concentration of X in the effluent from the secondary tank, and concentration of microbes in the sludge that is being wasted or recycled out here, right. These are the general terms. Let us move on. Here we need to understand two aspects. Until now we have looked at theta or TR, let us say, right. Different people use different variables. I typically go with theta. With theta, what is theta now? It is the hydraulic retention time, hydraulic retention time. So, it is theta is equal to V by Q, right. So, it is equal to volume of your particular system by flow rate. Q is flow rate is volume per time, let us say, right. So, it is at time, but it is not as if time in the general sense. This gives you an idea about theta, hydraulic retention time will give you an idea about how much time this particular water molecule or those compounds coming in with the water molecule will spend in your reactor. That is the hydraulic retention time. But here we have a new variable, solid retention time, which we are going to refer to as theta c. What is this now? Let us look at that. So, here is my aeration tank, water is coming in, water is going out. Let us say I know the Q, I know the V, I can calculate the theta of the compounds in the water or of water, theta equal to V by Q. But here in this particular process, activated sludge process, the system is not as simple as this. You know that from the sludge that has settled out, we are bringing in some microorganisms. So, as you can see here, the key aspect is depend upon how much microbes are present or how much time the microbes are spending in this particular reactor, let us say. So, it depends on QR, again QR is a factor, let us look at that later. So, here we are not just looking at how much time the water is spending in the system, but we are also concerned with how much time your particular microorganisms or which in layman's terms are referred to as solids here are spending in the system, right. How much time the microorganisms are spending in the system, theta c, right. Again that typically increases because we have this recycle flow. For example, if there is no recycle flow and it is just this, then theta will be equal to theta c, right. But in this case obviously theta is not equal to theta c. Why is it? Because the sludge is being recycled within the system, while some will leave the system from effluent or from wastage. So, in general theta c will be greater than or much greater than theta, let us see. Why is it? Again you want to have the microbes spend more time in the system, right, so that they degrade the relevant wastewater. So, these aspects we need to be clear about. Let us move on to the next aspect. Okay. So, as I mentioned, we are going to look at material balance. Before I look at material balance, let us understand the system. We have this water coming in, water going out, and this is the symbol that I am going to use for mixing while providing oxygen, and then I am going to have this recycle out here, right, recycle, and wastage and the treated water will go out through here, right. So, here if I look at this particular system out here, let us see, right. If I look at this system, right, the aeration tank system, what do I see? I see that flow is coming in and is bringing waste in, meaning mass is coming in, and flow is going out along with some waste, let us say. So, mass is going out and reactions are occurring in the system due to the microbes. So, mass coming in, mass going out and reactions occurring. So, again how are we going to analyze the system? By applying mass balance. So, here how do I analyze the system? Is it a batch system, as in is it a closed system? No, because mass is coming in and mass is going out. Is it a plug flow reactor? Well, with plug flow reactor, the concentration of the compound of concern within the reactor is not the same throughout the reactor, but here with continuous mixing, and the assumption is that we are mixing it homogeneously, we are assuming that the concentration is same within the reactor. So, it is not a plug flow reactor. So, what is the next aspect? Mass is coming in, mass is going out, reactions are occurring, and more importantly it is completely mixed. So, we are assuming it is a completely mixed flow reactor or continuously stirred tank reactor, right. So, we will apply the mass balance for this particular system, considering the system to be a CSTR or completely mixed flow reactor. What is the fundamental mass balance equation? Okay, not fundamental, the macroscopic mass balance equation. So, this is the accumulation term. How is the mass within the system changing, right? If dC by dt is positive, yes, it is increasing or accumulating. If it is negative, it is decreasing. Will be depend upon mass coming in Q in C in minus mass going out Q out C out plus volume into rate of formation minus rate of loss of the compound, let us see, right, or thus I can replace by R net. So, this is the mass balance equation we are going to use and apply throughout this particular what do we say session, let us say, at least for wastewater. So, let us see what are some of the aspects we need to be concerned about. As we discussed, we need to get the theta, we need to get the theta c, how much time do I need to let my water stay in the system, how much time do I need to let my microorganisms stay in the system, what should be the volume of the relevant system if my S in the effluent or waste in the effluent is 10 milligram per liter, I think that is our new standards. I think we looked at the standards, is not it? So, how do I go about designing these particular variables, let us see. So, we are going to apply material balance obviously, as we mentioned it is for a completely mixed aeration basin, let us see. So, we are assuming that it is at steady state, which is not a great assumption, but we are looking at the long term what do we say analysis. So, steady state in that context is a decent assumption. What are we applying the mass balance on? We are applying it on the biomass or the microorganisms, which we are referring to as the volatile solids, because that is how we measure that. Okay, volatile suspended solids, we looked at what do we say, a graph or a flow chart where we looked at suspended solids, dissolved solids and so on and so forth. Here we are looking at volatile suspended solids here, let us see. And what is the control volume? It is around the entire system. Why the entire system? As in, I know that this is my aeration tank and this is my secondary clarifier where the sludge is being settled down and the supernatant is going out. Let us see, why can't I just apply the mass balance out here along this or around this green colored control volume? Let us see. Well, in that case what is going to happen is I will have an additional variable, as in this Q recycle also will come into play. So, that will add to some complexity or unnecessary complexity. So, to make it simpler, if I choose my particular control volume to be this, right, this is my control volume, right. Obviously, I need to see to it that. So, this is wastage. So, what is it that I am just concerned about? Mass coming into the system, mass going out of the system, and mass being wasted from the system. So, these are the three aspects, and I do not really care what is happening within the system other than the reactions. Whatever flows coming, recycle flows inside the system, I am not really concerned with it. So, this is my control volume which we just defined, right. And here we are applying the steady state mass balance on the biomass or X. So, what is the mass balance? We looked at the equation, this is the mass balance, right. So, at steady state obviously this term is 0. Now, let us apply the other variables out here. So, dC by dt is 0. What is the concentration of the relevant or what is the mass coming into the system of the biomass? It is Q into X in, let us say X in, right. And what is the, how is the mass leaving the system? This is how the mass came in, Q comma X in, right, mass of biomass or the microorganisms. And how is it going out? Some will leave through here, Q minus QW and X effluent comma X effluent, and here it is Q wastage comma X recycle, let us say, right. So, it is mass is leaving the system via two means. So, minus because it is leaving the system, and one is Q minus QW into X effluent, plus how else is it leaving the system? QW into XR, that is how it is leaving the system. Are there any reactions occurring that can change the system or affect the microorganism concentration in the system? Yes, we know that microorganisms are consuming food, and then cell synthesis, reproduction and so on and so forth, or growth, let us say. I should not use the term reproduction, and also they are dying too, there is a decay too. So, yes, there is reactions are occurring that will affect your microbes. So, that is what I have out here, let us say, right. So, let us see what else I can do out here. Xn, as I mentioned, Xn little to no microbial concentration of use to us in the context of wastewater treatment comes in. So, I can assume that Xn is equal to 0, right. So, now what will I have? I can calculate Rx, which is R net X, I guess. R net X is equal to Q minus QW into Xe plus QW into XR by volume. Again, we are not going to mug it up. All the equations, general equations that are necessary will be given, but obviously I am talking about the exam here. The equations will be provided, but you need to obviously be able to understand what are the assumptions behind coming up with that particular equation. Why? Because we will ask questions or we have to analyze systems where the assumptions are not valid, and that is when you need to be pretty thorough, let us see. So, this is what we have, right. This is what I have out here, right. Let us keep this in mind. Let us say equation 1, let us say this is Rx net, right, and let us see. And material balance for completely mixed aeration basin, here let us say I want to look at the solids retention time. And what is the solids retention time, let us say, right, theta c, right, theta c. How do I get that? Earlier we were looking at volume by flow rate and such, but here it is nothing but mass by mass being removed per time, right. This is the mass of microbes or mass of the solids by mass of solids being removed per time, right. at steady state removal rate equal to production rate, fine. So, theta c in general terms is mass of the solids or the microbes in the system by the rate at which the what do we say microbes are being removed, let us say. So, how can I put that in or such? What is the mass of the microbes in the system, let us say. I know that the volume of my system is V, this is V is of the aeration tank, and let us say it is by concentration of the microbes is X, this is within the system, right, the entire system for which we defined the control volume earlier. How is it being removed? I know that mass is coming in, X is coming in via the influent, X is going out via the effluent and some via the wastage, right. How is it being removed? So, it is Q minus QW into X effluent plus what else is, how is it leaving the system? By Q wastage into XR, right. So, that is what I have out there, is not it. So, you can look at what I have out here, Rx net is this, and we have what is this theta c to be this. So, let us try to combine those two what do we say aspects. Okay, before I go further, what does it let us look at this under system and try to understand that. Okay. So, suspended solid at steady state removal rate equal to production rate, right. So, this links the solids retention time with the inverse of biomass produced, right, biomass produced per time per amount of biomass. For example, this can also be written as mass in system by mass removal rate and mass production rate, right. So, theta c when I say mass it is of the microbes, please keep that in mind when I say C, theta c cell retention time or solids retention time. So, theta c is giving me an idea about mass production produced or biomass produced per time per the amount of biomass in the system, let us see, right. And then combining this with equation 1 which we had earlier, what do we see? Rs is equal to x by theta c, I guess it should be Rx if I am not wrong. So, this should be Rx net, and combining equation 1 with the equation for theta c, this is what we get, Rx equal to x by theta c. Again, these are aspects we are going to use later, let us keep this aside, fine. Let us move on. So, now what are we going to apply the mass balance on? Substrate, not substrate, pardon me, suspended solids, steady state on the substrate around the entire system. Earlier we applied the mass balance on X, which is the microbial concentration or the biomass. Now, we are going to apply it on our waste or the substrate, right. Again, what is the system? The system is the entire system which includes both the aeration tank and the secondary clarification tank. So, I am not concerned with the recycle flow, I am only concerned with mass coming in, mass going out, let us see, right. So, let us just plug this in. Again, it is a CSTR, that is the assumption. Here again we are assuming that the reaction is only taking place in the aeration tank, it is not taking place in the clarifier. That is a good enough assumption because oxygen is only being provided here and no oxygen is being provided in the secondary clarifier. So, when we take the volume, effectively we need to take the volume of the aeration tank only, that is something to keep in mind. So, let us get on with it. So, we have mass V dC by dt, pardon me, because it is at steady state, that is equal to 0, that is equal to the waste coming in. So, I know its Q is the what do we say flow of waste water coming in, S naught is the substrate coming in, this is S effluent or S, let us say S here, let us say, right. We are assuming the same effluent substrate will leave via Q minus QW and QW, let us say, right. So, how is the substrate or the waste leaving the system? It is leaving via Q minus QW into S, that is what is happening out here. This is the treated waste water and some is leaving along with the sludge, let us see, right. Some is leaving along with the sludge, right. And what else? We know that there are going to be reactions occurring. So, I will say plus V into R net of substrate, right. So, that is something we have out here. Let us just try to analyze this system. As you can see, minus QWS plus QWS, they are going to cancel out, right. So, let us simplify this. 0 equal to Q S naught minus what am I left with, Q into S, that is what I have out here, plus V into R net of S. Therefore, R net of S, it will be equal to the negative of minus of Q by V, S naught minus S, and Q by V or V by Q, as you know, is theta, hydraulic retention time, right, hydraulic retention time. So, that is equal to minus of S naught minus S by theta. So, what does this S not S, pardon me, negative tell me? What does that tell me, right? It is negative here. It tells me that the net rate of waste or the substrate is negative. So, that means the substrate is being decreased, that is what it means. R net being negative means it is being removed. So, this is, let us say, equation 2 or equation 3, let us not keep track here. So, that is what we have out here, right. So, let us move on. So, steady state and such. So, this is negative out here, right. So, if you have or would have analyzed the system without the recycle, right. For example, we know that the system that we are considering has recycle here, let us see, but we are applying the mass balance around the whole system, right. Because of the way we are taking the control volume, what is happening within the system is not of concern. So, if you look at it, RS, right, is more or less same as the one for the system without recycle, that is what we have. Substrate balance is the same, biomass balance differs only in substitution, but again keep in mind RS, this thing will be the same, but if I am applying it on X, that will be affected, let us see, right. So, that we can what do we say, look at it, because there we have theta C, right. So, that is one aspect to keep in mind. Let us move on. So, what do we have here? We have material balance for completely mixed aeration basin. To get at the variables of interest, as in I need to be able to calculate S effluent, I need to be able to calculate the volume of the tank, theta C, I need to look at these aspects further. So, what is it that we are asking here or going to do? Kinetic equation for biomass growth, okay. In this context, I just need to what do we say, refresh your memory with respect to what we discussed earlier. In general, if A goes to products, what is the rate of this reaction, right? It is going to be equal to a rate constant times the concentration of A, right. So, here I am concerned about the biomass microbial growth in general, not a chemical, not in general it is not a chemical reaction. But let us say here I have X, which is the microbial growth, which is increasing, and the rate constant is mu, let us see, think of it, let us see. But where do we get this mu? We get it from the Monod kinetics or Monod equation, let us see. And how did this equation come out? Okay, let me not say how, what is it equal to? Mu specific biomass growth rate, let us see, right, is equal to mu max into S by Ks plus S. And how, if I plot this mu versus S, what is this going to look like? Obviously, something like this, and this is the mu max, right. And when S or what do we have here, Ks is when it is equal to mu max by 2, that is when we have Ks, let us see. So, one aspect we discussed earlier was that if S is very high, what will that be? S is far greater than Ks or S is very high, then S is far greater than Ks, SS cancel out. So, mu will be equal to mu max, right. And if S is far less than Ks, what is it that it will turn out to be? Mu is equal to mu max into S by Ks. Why is this relevant? We will just look at that. So, here I need to know rate of production of my microbes. So, that will be equal to, if I can say in similar terms, the specific growth rate, let us say, into the concentration of the microbes, right. So, if mu is such that, or in the case where S is very high, you will have mu max into x, right, meaning the rate of production of the microbes is just dependent upon the concentration of the microbes, that is it. This is the case when S is very high, but the other case when S is very low, especially compared to Ks, what will that turn out to be? Rate of production of X will turn out to be equal to what now? Mu max into S by Ks into X, meaning the microbial growth rate, right, will not just depend on the microbe concentration, but it will depend upon the amount of food available to that. That is the case when the substrate is low. So, these are the aspects we need to keep in mind, but again rate of production is what we have here. So, R net of X, let us say, is equal to rate of production of X minus rate of loss of X, let us say, and I know that what is this rate of production of X, right, this is what I have, is equal to mu X minus rate of loss of X, that will be depend upon the decay constant which we discussed earlier into X, right. And what is this Rx? Did we look at this or get this earlier? I think we did. So, let us substitute relevant variables out here. So, what do we have? Rx net is equal to mu times X minus Kd times X. What is this? Rate of loss of X, meaning death of microbes, and rate of production of microbes, right. How are the microbes being produced? By taking the food or the substrate, let us say, right. So, but did we calculate Rx earlier? I think we did. Let us go back and look at that equation earlier. Okay, Rx net equal to x by theta c. So, x by theta c is equal to, I will take x common out here, x common term out here. What is mu? We know that mu is equal to mu max into S by Ks plus S, and this is minus Kd. So, from here I can rearrange and solve and get this S, right. So, that will give me one of the variables of interest. Again, what is this S here, right? What is the S? S is the concentration of substrate within my particular aeration tank, right, which is more or less the same as what is going out, let us say, right. So, this is depend not on theta, please note that it is not dependent upon hydraulic retention time. So, the concentration of the waste or the BOD in the treated wastewater is not dependent upon theta, but it is dependent upon theta c, let us say, right. So, that is something to keep in mind, as in it depends on how long are you storing your microbes in your particular system, let us say, right. So, I guess we have more aspects, but I believe I overshot my particular time limit. So, we will continue this in the next session, but one aspect to note is that I am just playing around with variables, but we need to understand these underlying variables in terms of the mass balance. Why? Because most of the assumptions we use to look at the relevant equations are not going to be typically valid. So, only if you know the mass balance and how to apply it will you be able to play around with the variables pretty easily and get at the relevant variables, let us say. So, with that I will end today's session.